brute force to optimal to using bit manipulation to using binary search and to also using slow and fast pointers. We'll see all the approaches. That's the reason the video will be unique. So the problem says that we are given an array of integers called as nums. So we just have an array of integers. Now it contains n plus 1 integers where, so we have an array of integers called as nums and it will contain n plus 1 integers. So n plus 1 integers I will have, and the integers will be in the range of 1 to n. So remember, I will have n plus 1 integers, but the integers will be in the range, the number of the integers will be in the range of 1 to n itself. Now it just says specific one thing, that I have only one repeated number in my nums. I have only one repeated number in my nums. Again, please make sure that these small things will add up. So I have only one repeated number. Again, you can ask a counter question to the interviewer, that what is the frequency of the repeated number? That can be a question for you. So make sure that you ask these questions in an interview. Now my problem is to find, just find out that one repeated number, what is that number? And the problem says that you must solve the problem without modifying the array nums. So one thing is, I cannot modify the array nums, and I should also try to use only constant space. So as you can see in this example, my repeated element is a 2. So I can simply say my repeated element is a 2. Here I'll see my repeated element is a 3. Again, so when you would have asked the interviewer, sir, what is the frequency of the repeated element? Because interviewer said that element can be in the range of 1 to n. I will have n plus 1 elements, but repeated element can have any number of frequency. So you will see that my repeated element can be all of them also. This is what they have also clarified. All the integers in the nums appear once, except for precisely one integer which appears 2 or more times, right? So all the integers will appear. If there are some integers, they will appear only once. Apart from this, the repeated integer will come 2 or more times. Cool, great. So that is one thing, and for sure make sure that nums of I is less than equal to n, because nums of I is in the range of 1 to n. Now very normal, very obvious approach is that we know that we have repeated elements, right? We have repeated elements, so I can just simply say, okay, if I am at the index, let's say 2, I will search for index 3, 4, 5, 6. Simple. I'll keep on trying. Let's say I am in index 1. I'll say, okay, is there anyone equal to my value? Okay, no. Is there anyone equal to my value? No. Anyone equal to my value? No. Anyone equal to my value? No. Anyone equal to my value? So this will keep on checking. So at every index, I'll keep on checking other indexes to see if someone is equal to my value or not. So I'm just using 2 for loops to just figure out or make a pair of equal values. So what I'll do is I'll simply go on and simply apply 2 for loops, okay, from 0 to less than length and from I plus 1 to less than length, which means my I and j will try for all 2 possibilities of I and j. If they are equal, voila, I have found the answer. So I'll simply return that specific integer which is repeating, because I know that only one integer will be there which is repeating, and I have found that one integer, so I can simply return in this answer. So you will see, as you are using 2 for loops one side another, you are bringing out and making all 2 possibilities of your pairs. So for sure, time is O of n square. Space is O of 1, for sure. Can you optimize it? Yeah, for sure. Obvious thing, we can optimize it. How? We know that all the elements will have one frequency. Just one element will have more than one frequency. So ultimately, it's everything revolving around the frequency, right? So what I'll do is, I'll just keep a map. This map will contain the frequency of every element. So I'll just go, okay, map of frequency of 1 is 1, frequency of 2 is 1, frequency of 7 is 1, frequency of 7 has become 2. Frequency of any element, if it becomes more than 1, I can simply return that element because it is the repeated element. So this is what I'll do is, and now to keep the track of frequencies, you can either use a hash map, an array, or a hash set. But bhaiya, how? Okay, hash map and hash set I know, but how we can use an array? Because you know the elements, which means 1, 7, 2, 7, this will be bounded by the n. So my elements inside the array will not be greater than or equal to n. So I can make an array of size n, and then I know, okay, my array is of size n. Now array will handle, or basically array will act as a element, like array will act as a hash map to keep track of the frequency of elements. So I can use all three possibilities. Do tell to the interviewer that what all possibilities you can think of storing the frequency of an element, because not every time you can use an array. And in sometimes, let's say counting sort and stuff, arrays are much more beneficial if you want to have ordered elements. Right now, what we can do is we can simply have the count. Now this count, we can simply go and say that, okay, I'll simply go on to all of my elements. Now if I go on to all of my elements, I'll simply keep on increasing the count. As soon as I'm increasing the count, I'll check if the count becomes more than 1. That is my repeated element which I wanted. So simply return that specific element. So you saw that you are using a time of O of n and space of O of n because of using a hash map or a hash set or an array. Now you remember the problem was saying that can you do this in a constant space? So now my problem starts off that can I do it in constant space? So again, there are a few solutions which are modifying the input array that I have skipped it because the problem was saying that you should not modify the input array itself. So there are a few solutions which actually can modify the input array, but we have skipped that. We will go on to a next non-obvious solution in this case, which is a binary search. So although we had a O of n time, we had a space of O of n. We wanted to optimize the space. Maybe the time might increase, but let's say we can optimize, we can balance it. We are increasing the time a bit, but we can actually optimize the space. So let's see what we can do. So again, thinking of a binary search in this problem might not be intuitional. So again, it is good if you have seen the video, you will be knowing it. If someone has not, then he will have a hard time coming onto this approach. So this is the non-intuitional approach. What we can do is, okay, we know the elements are in the range of 1 to n. That I was for sure given. And I know only one element out of them is actually repeating. So I will just do a binary search on that element itself and ask, what is that element which is repeating? Now bhaiya, how we can do it? As simple as that. Now in a binary search, usually you land onto a mid. Let's say you just simply number the element from 1 to n, 1 2 3 up till n. You will land onto a mid. Now mid will be, let's say, 5. So you will go and ask your actual input array nums that, bro, how many elements are smaller than my mid? He will iterate on this entire nums and will give you, bro, I can see, okay, 1 is smaller, 2 is smaller, 4 is smaller, 3 is smaller, and 5 is smaller. So I know, okay, I have 5 elements which is smaller than my number 5. You saw 5 elements, just a simple pigeonhole principle. Okay, if I have 5 elements, I know, okay, number 5 is number 5, which means, okay, number 5, how would a number 5 would have come in? 1 2 3 4 5. Now I am saying I have exactly 5 elements less than my this number 5 itself. So I have 5 elements and that is also equal to number 5, which means for sure every element will actually be unique. No element will be repeating. So I just wanted, and I am just figuring out how many elements are smaller than 5. And I got 5 elements which are actually smaller than 5. So okay, which means the repeating element is actually more than 5. So I will discard this left range because I know for sure that all the elements on the left side are actually unique. The repeating element are actually in the right side. So I'll now search for the right array, and you will also see the same fact that the element 7 was the element which was actually repeating. So that you will know that, okay, if it is equal to 5 only, then we know that we don't have any duplicate values. So we will try for the right range, which is from 6 to n, and in that I can simply do again a binary search. So if I just write the same algorithm again, low is 1, high is my length minus 1, because you remember length is actually n plus 1, and I know in my array I have elements from 1 to n. Now by default answer can be 0. Now our simple formula of binary search, while low is less than equal to high, and if our conditions satisfied, then we make our low equal to high plus 1, sorry, low equal to mid plus 1, and if not, then okay, I'll firstly put my answer as this. Okay, my answer can be mid, and then I'll say, okay, I can try for a lower high. which means high equal to mid minus 1. This is the by default template of a binary search. Now coming on to the actual condition in the binary search, firstly I get the mid, which is simple, low plus high by 2, but usually just to avoid our integer overflow, we write as low plus high minus low by 2. This is how we write. And now I just simply have to go and count of the elements which are less than, count of all the elements which are less than my specific mid which I have chosen right now. And I'll simply keep on increasing my count, keep on increasing, keep on increasing, keep on increasing, keep on increasing the count. If this count is less than mid or less than equal to mid, which means okay, for sure my repeating element is actually in the next range, which is low equal to mid plus 1. And if this count is already, if the count is big, which means okay, if the count is big, which means I have a repeating element in my this range, so I'll just say okay bro, my repeating element is in my left range, so I'll just reduce my high. And that's how I can simply solve it in O of n log n time. How time? N log n, because you saw that you are doing a binary search on this entire array from 1 to n. So log n will come from here, and for every mid element I am going and checking the count of elements which are smaller than the mid. That's a n. So that's the reason my time is n log n. Space I reduced, but I increased my time. Is there any way I can actually help and I can actually do it? Maybe, maybe not. But before that, there's another technique which interviewer might can jump you. Again, the complexity, we are trying to optimize it. Ultimately, our goal was to optimize my space, but in that we thought, okay, binary search is one solution. So can we use something else? There's another technique, bit manipulation technique. Again, these you can skip it also, but I highly recommend to watch it so as to get understanding of binary search, bit manipulation, and also slow and fast. So by this what we can see that okay, again, it is not intuitional at all to come up to this specific approach. This can say okay, if I can convert my numbers to their binary forms, and then from that if I can able to figure out what is the bits which will be left. So let's imagine that my nums have repeating elements as 3 1 3 2 3 4. I know my repeating element is a 3. Rest all elements are unique. Okay, 1 2 and 4. Now let's imagine my original array which I could have expected was 1 2 3 and 4, all elements occurring just once. But bhaiya, earlier you were saying that all can be 3 also. Yeah, that is something with because repeating elements can have any number of frequencies. But let's imagine right now the repeating element has just 2 frequencies and rest all elements are just occurring once. Right now I give you a task, bro. You have to figure out, okay, I'll give you okay 1 2 4 1 2 3 4 1 2 3 4. So you just know okay, one of the elements is repeating. So you have to just figure out what is that one element which is repeating. Again, there is a condition which you will see that okay, element repeating is only of frequency of 2. So bit manipulation, which means converting the numbers to binary form. Now very obvious which you have spoken is bhaiya, what I can do is I can just take its sum, I'll subtract the sum and then I'll get the answer. That is one approach which can be true only when the frequency of the repeating element is a 2. But as soon as the frequency will change, it will not become true. But the approach which we gonna see with bit manipulation will be true in both the cases. Let's see how. So we'll convert all the numbers in the form of bit and then we'll keep on tracking their frequency. So okay, firstly I encountered the number 3. Then I convert that number to a binary form 0 and 1, and then I actually am maintaining that count of bits at a specific location. Okay, at the 0th bit so far the count is 1, at the first bit so far the count is 1, at the second bit so far the count is 0. Okay, as soon as I encounter the next element which is 1, okay, 1's binary form is 0 0 1. Now I'll add this to my previous bit count. Okay, I have got a 0 1 2, then I'll get a 3 again. 3 converting to binary, it's a 0 1 1 again. I add that to a bit count, I'll get a 0 2 3. Again I get a 2. Okay, I'll get a 2, then it is a 0 1 0. I'll add that to my existing binary sum, I'll get a 0 3 3. Then I again went back, I have last element as 4, converted 4 to a binary, it is 1 0 0. Add that, I'll simply get a 1 3 3. So the binary representation sum of all these numbers of my nums actually has become a 1 3 and 3. 1, 3 and 3. Now imagining that my original array would have been a 1, 2, 3, I'll do the same process for him. Okay, again, it 1 entered, it will be a 0, 1, 1, then 2 entered, sorry, then 3 entered, then it will be a 0, 1, 1. So I'm just simply adding all these elements. So the sum I have got here is 0, 1, 2, 2. I have got a 1, 2, 2. Now, as we were simply saying, bhaiya, I'll simply subtract. Yeah, you can simply subtract here also. So if I subtract from this to this, I'll simply be remaining with a 0, 1, 1, right? And that 0, 1, 1 is actually nothing but a element which was actually extra or repeating. So this is how we can handle it, and it is the same which you're also thinking, but yeah, I'll simply, rather than converting to binary, I can simply add these numbers and then get the answer. That's true. But now this was the case when I had only repeating element as 2. Now this condition can actually help us when the element repeating are more than 2. How? Let's see. So right now we saw that, okay, we can just convert that to an integer back. But let's say now the element 3 is repeating many times, right? Now by default, my original array, I was expecting it to be a 1, 2, 3 and 4. If that was the case, then for sure, if I convert it to a sum, I took a binary sum for this, I'll get a 0, 4, 5. If I convert this to a sum, binary sum, I'll get a 1, 2, 2. Now, if I go and do the subtraction, I'll do a -1, 2 and 3. Now, what these actual things means? What does -1 mean? After subtraction, if I'm getting, okay, 0 minus 1, it's a -1, 4 minus 2, it's a 2, 5 minus 2, it's a 3. So I know, okay, I have got something like this in my after subtraction. Now I know one thing, okay, if something is negative, right, if something is negative, which means it would be coming from my this specific thing, right? If something is positive, it would have been extra in my nums, right? So, and again, I wanted the thing which was extra in nums, because I made sure while generating my original array sum, I made sure nothing is extra, right? So whatsoever is positive, which means whatsoever is extra, would be for sure coming in from nums. So I will just take this specific thing, okay, whatsoever is positive, okay, the 0th bit is positive, for that I'll keep a 1. The first bit is positive, for that I'll keep a 1. The next bit, which is the second bit, it is negative, keep a 0 for that. Now I will actually form this number, and then I can convert that number to an actual number, and then that will be my answer. That is how I can actually get this solving. So that is the reason how converting to the binary form and then subtracting made me sure, okay, if this is negative, it would for sure be coming in from my original. If it is positive, then it is coming in from my extra thing, from my nums vector. And that's how I can simply solve it. Now that is another way to solve it, but you will see the time complexity of this also will actually be O of n log n. But bhaiya, how O of n log n? Because every number of size n, if you just imagine a number, let's say n, it can have log n number of bits, right? So if I, let's say, if I give you a number, let's say n, so you know, okay, n to relate to reach power n, you'll just try to see 2 in the power of 2, you'll write that stuff that can have log n number of bits, and for sure you'll go on to every integer. That is just to find the sum of the bits and all this stuff. You'll go into every integer. For every integer, you're going to all the bits of that integer. So log n bits I will have, and I'm going to every integer. So the time complexity O of n log n. Space is again O of 1. So it is same as that of the binary search approach which we saw above. Let's have a quick glance at the code. Again, this is not required for you to understand. It's just that it will help you in the interviewer, if the interviewer is mind fucked, and also it will help you to get good at binary search and bit manipulation. So we saw that firstly we will have to grab out, okay, bhaiya, how far do I have to go? Because I generally know that I have 32 bits, right, in my number, which is actually less than 189. So shall I go to all 32 bits? I said, okay, we can have a bit optimization. If we know what is the maximum number in my entire nums, right, from that maximum number, I'll grab the bit maximum number, I'll grab the maximum number. From that I'll grab, okay, what is the maximum number of bits required to go up till, right? So what I'll do is I'll simply grab the maximum number. So this will simply go and find, okay, what is the maximum number in the entire array of nums. I've grabbed the maximum number. Now this is only useful just to grab out the maximum number of bit required for me to iterate. So I just went on and passed this maximum number in this calc max bit function. This will go and find simply going on to every of my number, like every of my bit, and up till what point I can go, I'll just simply keep on increasing my bit count, and by this I will get maximum number of bits in this maximum number. Now if you don't want all this headache, you can simply make this as a 32 also. It will still work, because for sure you can just taking the upper limit for all nums. Even if my nums maximum number is, let's say, 5, or even if it is 100, you are still taking 32. So that's one case. Then again, as I told you, that you will just have to find out this subtraction, 5 minus 2. If it's a positive thing, then for that I will simply have a 1 in my answer. So what I will do is I will have to find, okay, this 5. Now this 5 is nothing but 0th bit summation of all the numbers of nums. So I will go on and say, okay, for the 0th bit, give me the summation of all the values. Okay, I'll just go and check what is, I'll go and ask my first bro, what is your 0th bit? It is 1. Yeah bro. He will say, yeah bro, it is 1. Okay, simply I'll add a 1 in my answer. Is it 1? Yeah, add 1 in my answer. Is it 1? Yeah, add 1 in my answer. Is it? Yeah, is it? So he will give me a 5, right? I'll simply go and, okay, because the first is the 0th bit. First is the 0th bit, which I want to find out this sum. And then the same I will do for my original. I'll ask him the 0th bit. He will say, yeah bro, it is 1. I'll ask him the 0th bit. He will say, bro, it is 0. I'll ask him, it's 1. I'll ask him, it is 0. So my sum here will become a 2. So I've got the 0th bit sum from the original, 0th bit sum from my nums, and then I can simply subtract this, which is 5 minus 2, to get the 0th bit of my expected, replicated, duplicate number. If that is positive, then I can actually add a corresponding 1 corresponding to that specific bit. So what I will do is, I'll simply go on to all of my bits, starting from the 0th bit up till the maximum bit. For every bit, I will simply make a mask. This is how we generally propagate to make a mask. And then from the mask itself, you can actually derive if that specific bit was set or not. What we mean by that is, if I have a number 5, which is 101 in binary form, I make a mask so as to know if the 0th bit is set or not. I will do a 1 left shift my 0. 0 is this 0 and 1 is simply a mask element. So it will make a mask of 1 0 0 0 0 and all zeros. So if I do a AND operation with my element, so I will be able to figure out if my 0th element, because I made a mask corresponding to my 0th element. Mask is made, mask this, now I'll do a number element mask, but the mask is made by saying 1 left shift by the bit for which you want to find, the actual value or the position or the actual value at that specific bit. So this will replicate whatsoever is here. Here is a 1. Everything else will for sure be a 0. So with this, you will be able to figure out, bhaiya, what if it would have been a 0? Then your answer entirely would have been a 0. So if you want to know if the specific bit is set or not, you can use a mask for that. And after doing an AND operation with the mask, if the value comes 0, which means that specific bit was not set. If the value comes as a non-zero, you are not concerned about the actual value. If the value comes as non-zero, it means that bit was actually a set bit. And that would be, which means the bit which you are trying to consume. Now, coming on back, what we can simply do is we'll go on to all of my numbers, because I mentioned, right, for this specific bit, I want to find the count in my nums and count in my original. So I will go on to all of my numbers, and then I'll simply go and check, okay, I and mask, it is the original count, right? And nums of I and mask, it is the nums count. I'll subtract nums count minus base count if this thing is positive. So I'll just simply say that nums count if it is more than my base count, which means nums count minus base count. If it is more than 0, then I can actually, corresponding to this specific bit, I can add in my answer. So I'll simply say duplicate the number which I am expecting to be a duplicate number, I'll OR with the mask, because you remembered mask contains a 1 at that location. So in my duplicate element, I will have a 1 at the 0th bit corresponding to that, because you remembered if something is positive corresponding to that bit, you need to have a 1. So that is what I am making with my duplicate number. That is how I can simply solve it with the complexity of O of n and O of 1. But now comes the most interesting part, which is how you can actually solve it in the best possible time. It is O of n time in O of 1 space. So if you remember one fact, we specifically mentioned that we will have a duplicate element. Now, how we can, again, this is again non-intuitional, because we will use a slow and a fast pointer. Again, if you know this, you will be very good in an interview. If not, then you are screwed up. So what we can do in this, we know that, okay, we have an element which is repeated. So for sure, if something is repeated, which means if I start making a cycle, which means, okay, I will have a 0. Again, you in the very beginning might not understand why a cycle can be made. But if you just go back and think that if I start off by making a cycle and say, okay, from the index, I will make an arrow to the element. And the element, I will just again assume that as an index, which is this, index 1. And then again, I'll make an arrow to the element. So if you saw, okay, index to element, and we remember elements are repeating. So for sure, index to element, element can be repeating. So this two can be same. If this two can be same, so I can for sure form a cycle. That is with the fact, okay, with the reasoning that, okay, how we can actually think of that it can form a cycle. Now we know that, okay, it will form a cycle. What we will do is, okay, I'll just try to replicate. Let's form a cycle itself. So, okay, index 0, I pointed to 1, which means index will point to his element, and element will imagine him as the index itself, which will point to his other element. 1, it went to index 1, pointed to 2, it went to index 2, pointed to 7, it will go to index 7, point to 5, it will go to index 5, point to 4, it will go to index 4, point to 6, it will go to index 6, point to 3, it will go to index 3 and point to 7, it will again go to index 7 and point to 5. You saw? Index 7 I could reach also from here, and index 7 I could also reach from here. Thus, I will form a cycle. Now, that is for obvious because I have a repeating element. If I would not have a repeating element, so there may or may not be chances of actually getting a cycle. Now, if I have a cycle, I know the element is repeating. So for sure, and again, it's just a one element which is repeating. If something you have as a cycle, and you know only one element is repeating, so only one element will be there who will have, okay, incoming edge, outgoing edge, and again an incoming edge. So that will be an intersection of edges. So I got to know, okay, only one element is actually unique. So he will be the corner element. Basically, he will be that intersection element for me. So now my ultimate goal has become, I just have to figure out what could be this intersection element. Now, if you had learned in the linked list, you would have known that to find this intersection element, right, we used the slow and fast pointer technique. Again, we will see the proof of this also, but yeah, let's see what slow and fast pointer actually mean. So slow pointer means that, okay, I'll move my, if I just name my pointer as a slow, so I just move it one step, which means, okay, if my slow is here, it just moves in one unit of time, it moves one step, just one step, it becomes here. But my fast pointer on the other hand moves two steps. So if my fast pointer was basically here, so it will try to move, okay, one step here, other step here, it has moved two steps. So you will see that fast pointer will become 1 and 2. It has moved two steps. That's how a fast pointer moves. So now you saw. And bhaiya, what is this you wrote? Okay, this you got, this you made, that is understood. But what is this you wrote? If you remembered, we are actually moving in indexes to values to indexes to values. So that is what I have written, that, okay, if I have, let's say, if I put my slow as a 0, so nums of 0 is a 1. So you saw, okay, if my slow is a 0, so Nums, as you can see, slow is a, I'll just erase this entire thing. Slow is a 0. So that nums value is a 1, which means the next step is a 1. Okay, slow value is 0. Nums value of that is actually a 1. So slow is now a 1. One step movement. My fast was also a 0 in the beginning. My fast was also a 0 in the beginning, but fast will move 2 steps. So fast, which means slow, which means fast was 0. Then he will go on to 1, which means nums of fast is a 1. Then again he will go on to this value and again find the nums of that. It's a 2. So nums of again that value, which is a 2. So that's the reason it can move to 2. That's how I fast my move. Fast will move 2 steps. Now bhaiya, okay, that is, you showed that okay, slow and fast will propagate one step, but how in the entire array it will propagate? Simply just a do while loop. That okay. Now bhaiya, why not a while loop? If you even do a while loop, then you will have to just put a condition that in the beginning he should actually be moving 1 step, he should be moving 2 steps. That is, you have to put a condition, right? Okay, do while loop, because with the do while loop they will for sure will move 2 steps. But bhaiya, okay, I still didn't understand that why while loop is not useful. Because if you do a while loop, what will the condition you will put? Condition is slow is not equal to fast. In the very beginning, both slow and fast are same. So that is the reason I'm saying if you are using a while loop, then it will not even start, because you are starting from slow and fast being same itself. So you have to use a do while loop. Or if you don't want to use a do while loop, you can actually say, okay, firstly move your slow 1 step, firstly move your fast 2 steps, so that both of them become different, and then you can start using a while loop. Now in the loop itself, I'll simply keep on moving my slow 1 step, fast 2 steps, and as soon as they meet, I will have to stop. If I don't stop, the loop can go on infinitely, because you know it is a cycle. So it will keep on going. Okay, now I have known that okay, I will just do a slow and fast. I know that I will have to stop when my slow and fast will move. Sorry, when my slow and fast will meet. Now, as you remembered, my slow and fast were here. My slow moved 1 step, my fast moved 2 steps. Now I am here. Again, it will keep on going until they will meet. Okay, slow will next move here, fast will move at 5. Okay, slow has reached here, fast has reached here. Again, slow will move 1 step, fast will move 2 steps. Slow has reached 7, fast has moved 6. Slow will again move 1 step, fast will again move 2 steps. So slow will reach here, fast will reach here. Slow will move 1 step, fast will move 1 step. Both of them will land onto a 4. And that's how my condition will break, because I wanted as soon as both of them will actually meet, I will have to stop. Now bhaiya, again, your actual aim was to find this number 7. What you did by stopping at this location, this is not the answer. You still have to figure out the number 7, because that is the answer you have to return. Yeah, that is true. So what I can do instead is, okay, I can easily see with the diagram, right? With the diagram, I can see both my start pointer, from which I have started in the very beginning, which was actually 0. It will always remain a 0. And my meeting point of my slow and fast pointer, both are at the equal distance to my intersection point. So what I can do is, I can imagine, okay, my start point as let's say SP and my meeting point as let's say MP. So I can keep on moving them 1 step, 1 step, 1 step, 1 step, 1 step, and 1 step. Oh, as soon as my start point and meeting point will meet, both of them will keep on moving 1 step, 1 step, 1 step, 1 step. As soon as both of them meet, that will be my intersection point. This is what we got to know by the diagram. But bhaiya, is it always important? Yeah, it will be. Let's see the proof of this. So what we got to know that, okay, we can initialize our slow variable after we have got the meeting point, which is this meet point, right? So we know that is a slow and fast meeting point. This is a start point. So I can initialize my pointers back to, okay, I'll initialize my slow. I'll not make any extra new pointers. I'll not make a start new pointer and a meeting new pointer. I'll use the existing pointers, which was slow and fast. I'll reinitialize my slow back to my 0. I'll have my fast at the same point, and then I'll keep on moving them one step. And wherever they will meet, that will be the repeating element. Now, the code will look as simple as that. You initialize your slow to 0. Your fast is already pointing to this location because you didn't change it. So you'll keep on moving both of them one step. Again, you will see now both of them are moving one step, one step, one step. And I know as soon as both of them are moving one step, at last, both of them will be pointing to my, as soon as they will meet, both of them will be pointing to my repeating element. And that's going to be my answer. But bhaiya, what about the proof? Yeah, proof is as simple as that. Now, let's imagine you had a start point. The meeting point or the collision point was x steps apart. This was x steps apart. Let's imagine that. And my duplicate value, which means my intersection point, was actually saying y steps apart, right? I know I will form a cycle for sure because I have a repeating element. Okay, great. So I know that, okay, if my slow will start, my slow will travel x distance. In that time, as my fast travels twice as that of slow. So for sure, if my slow traveled x distance, as you saw, my slow traveled x distance, so my fast in theory would have traveled a 2x distance. Again, in theory, that would have traveled a 2x distance. So if I bifurcate that, okay, I know that the entire thing was x from here to here. So if I imagined the starting to my intersection point, I said that, okay, it's a y. So for sure, the remaining portion will be x minus y. And if you remembered, I am saying that the fast would have been traveled at 2x. And we remember that they meet at the collision point. So for sure that the fast will travel like this. It will travel, and then it will meet. Correct. So you saw that the fast is traveling like this entire thing, right? This is how the fast is traveling. So if I just want to say that, I will say, okay, fast entire thing is 2 into x. So if I just remove this part, this portion, I know this is y portion. So this entire portion, I'll just put it as a green color. This entire portion is a 2x minus y. So this entire portion is a 2x minus y. Now great, I know this is x minus y because this entire thing was x. I know this entire thing was a 2 into x. So for sure, this entire thing is a 2 into x minus y. So I have got these two values. Now I'll simply do one thing. I know that I will be having this cycle, right? So I want to know the cycle length. So I'll just simply say, okay, I know this specific path has a length of x minus y. This you can see, okay, it is overlapping repeating part, right? So in 2x minus y, if I remove this x minus y, so I'll remove one of the white lines here, right? So I will form just one circle completely. So I'll just subtract 2x minus y minus x minus y, I'll get a x. So for sure, this cycle length, again, I'll just not erase this cycle length from here to here, the cycle length is actually a x. But right now we just said, okay, it's a x. It can be a multiple of x also if my cycle is very small, as in if this entire thing is very large. So it will keep on moving, my fast will keep on moving. So it will be, my cycle length will be a multiple of x. But right now we can imagine this as a x also. So right now we have got to know one conclusion that, okay, my cycle length is actually a multiple of x. Now when this is the case, we know one thing, okay, cycle length is actually my x. So, okay, now I want to know cycle length, this entire length is actually a x. And this entire portion is x minus y. So what is this remaining portion? It is x minus this value. So I'll do a cycle length, which is the entire cycle length. I'll subtract this entire length. I'll get this entire length. That is it, right? So I'll just subtract my x minus y, which is this specific length, from my cycle length, which is x. I'll get a y. So I know, okay, from 4 to actually intersection point, the distance is a y. And if you remembered, I had assumed from my starting point to my intersection point, it's also y. So this is how we can prove that, okay, from this meeting point and from the starting point, intersection point are always at the equal distance, that is y. And that's how I can actually prove it. And with this, you are actually doing just one pass, and with that, no space used. So time is O of n and space is O of 1. Let's see the code. It's pretty simple. As we saw that we initialize a slow and fast pointer, both pointing to 0. If you remembered, both are pointing to 0. If I just show quickly, both are pointing to 0. And the code will also be same, exactly same. This is how my slow and fast will move, but I will use a do while loop instead and will try to move my slow and fast. Now when this will move, I'll remember my slow and fast will meet at the meeting point. Now this is my meeting point. From meeting point and from starting point, Starting point is a 0. Meeting point is where the slow and fast already there. So I'll assign my slow to my starting point. I'll keep my fast here, and then I'll keep on moving one step. So again, when they will both will move, they will actually meet at the intersection point. So if I come back, I will actually use a do while loop to actually make my slow and fast both reach to my meeting point. As soon as both have reached there the meeting point, I'll initialize my slow to a 0, saying my slow is at the starting point now, my fast is at the meeting point itself. I'll again move my both slow and fast so that equally again one step equally, so that both of them will actually meet at the intersection point, which is nothing but my duplicate value. And that's how I can actually reach and say it is my answer with just O of n time, because you are going on to every element exactly once, and spaces O of 1. And that's how you can simply solve it in 5 ways we saw, from brute force to using a map, to using a binary search, to using a bit manipulation, and ultimately by using a slow and fast technique. I hope that you got it. Bye bye.